Well, in this video, we are going to see how to create a nonlinear analysis with a more detailed perspective, so paying more attention in the different options. First, we create analysis and we add a structural nonlinear command. The command is composed by 5 different sections where we have to select different options on each one. So the first one, evaluate the model, is something that you by default don't need to touch, but it's useful when you make some changes on the model, on the mesh, and so on. So you need to reassemble all the matrix and recalculate the load vectors and the stiffness matrices. So this is something that you need when you do some phase analysis, for example, or something like that, and you need to do always at least once. Then in the nonlinear effects, we have different options. We can include the different kind of nonlinearities in our model. We can include physically nonlinear or physical nonlinearities, geometrical nonlinearities, and then transient effects. By default, we only work with physical nonlinear because we don't need the geometrical nonlinearities except if we have a specific problem that it's a real relevant aspect to consider. And then the transient effects are meant for temperature and other effects, so it's not just a typical structural analysis. So if we focus on the physical nonlinearities and we open the different options that we have, you can consider many of them. You can consider plasticity, creep, cracking of concrete, total base cracking. So we have different ways to consider the cracking, nonlinear elasticity, hyperelasticity, but many of the options. So by default, you should allow all the options on, or you just left all the options activated. But in some situations, you could need to activate some options. For example, the creep option and viscoplasticity option can generate conflict if we are working with a specific creep problems, depending on the material model that we choose. Well, which nonlinearities you will allow is something that you have to consider regarding the kind of problem that you are working with. But by default, you can leave everything checked because it's not common that the different options can interfere each other. So just have this on mind. And if you have problems, consider that maybe the problems are coming from here. So we can move to the next step. That is the execute block. Here we have also different options. We have 4 different sections. The most important ones are the first and the second. In the first section, we work with the load cases and the load combinations, and then we define the different load steps. So here first we need to choose the load combination that we want to apply on our structure that we have previously defined in the model development. When we have the load set chosen, we need to decide how do we want to apply this load over our beam during the analysis duration. So in that case, we need to define the specific size of the loads. As you know, we need to define how much load we want to apply. So we can apply one time the defined load, or we can apply 10,000, 100 times. So it doesn't matter. It's up to us. So we can just define a load with a value 1 Newton divided meter, and then we can apply 8,000 times this load in one step. So that means we are applying 8,000 newtons meter. So this size of a step and the amount of steps is going to be related with the load that we define. In our case, we have defined the load with the real value. So our intention is apply one time this load. To do that, you can apply the load in one step or in different steps. If we want to define, for example, 10 steps, we need then to discretize the load in different steps, and then we have to divide one time divided 10. So that means 0.1 times the load each step. And then here you can also define different discretization. So if we want to apply, for example, 3 times the load in 2 blocks, we can define 0.1 10 times, and here 0.05 20 times. So this in total will would apply the load 3 times, 1 time in 10 steps and 2 times in 2 times in 20 steps. In total 30 steps and 3 times the defined load. And you can do that as many times as you want. So, and then also you can remove part of the load. Now if we want to bring back our structure to the one-time loading, we can just remove 20 steps of load, or even 25, and we will get then just half time the defined load. Then you can select different options here, like arc length control, that will help Diana in some situations to approach to the proper solution. So this is usually necessary when you have very complex loading problems and you have convergence problems. By default, it's not necessary, but depending on the case that you are working with, you need to use this option to increase the possibilities to get convergence in the model. In that case, all the 2 different blocks became in one because we choose the same step size. But if we instead use 0.05 and we apply, for example, 10, doesn't matter, half the load. When we go out, it doesn't become in one, so it doesn't merge. Yeah, the steps can be defined at automatic step sizes, so you can allow Diana to discretize your load, and it can be done using different options, but it's something that we don't recommend. So we think it's better to define ourselves which load we want to apply on the beam. Then we have full control of what is happening on our model. So, but just you to know that you have this automatic step sizing option, but yeah, we didn't have really good experiences with that, so we strongly recommend to use your specified size steps. So then can we move to the next option, that is equilibrium iteration. Here we have different options also. This menu is essentially defined to tell Diana how do we want the computational core to approach to the solution. So as you know from the lectures, there are many different ways to approach to the solution to solve the nonlinearity of the problem, and Diana has implemented some of them. So if we open this comic box, the first one, we see that we have Newton-Raphson, that it's the most common way to solve the nonlinearities of the problem, so to approach to the different solutions. And this is the most common because it's the fastest, but that doesn't mean that it's the better, because that's or it's the best, because that depends on your problem, as almost everything in finite element models, but it's not as robust as others, like the second quasi-Newton. So the robustness of the method depends on how the method approaches to the new iteration, to the new guess of solution. And Newton-Raphson does it quadratically, and then the second method does it linearly. So it's slower, but it's more robust in terms of efficiency to find the new solution. But which methods do we need to approach to our solution? It's strongly dependent on the problem. It's strongly dependent on how steep is or loading of the or how stiff is our beam, for example, how fast we reach the maximum load, how much plateau do we have at the maximum load, if we have a lot of yielding. So there are many factors that can influence these choices, but yeah, by default we just recommend to use Newton-Raphson and change it if we have specific convergence problems that we know that can come from the solution or from the iteration method. The other options in this frame of configuration are all of them related with the iteration method. So we need to define how many iterations do we allow for the iteration, to find the next solution, and then how we want to approach to this new solution. So we can choose different configuration options. The most relevant options is how do we want to get the first iteration. That's going to condition pretty much the next solutions that we find in the different iterations. And then we can just activate, for example, the line search if we have a possibility to have a snapback in our model or in our structural behavior. And then the continuation iteration. That just means if we don't get convergence, what happened? What do we want to do? If we say that the solution is accurate enough, or we don't accept the non-convergence solution to proceed with the next step. So in some situations that we know that we can have a specific problem when the beam cracks, for example, we maybe are interested to see what happened after this cracking, and we just jump the problem by continuing iterating, even if we don't have convergence in the previous steps. Usually we have 100 or even more iterations steps. That depends always, again, on the complexity of the problem, but 200 steps is not, it looks like that a lot, but it's not a crazy number. So in some situations you will need that much of steps to reach a good solution. And then in the second frame of options, we have the option related on how do we want Diana to say when the solution is good. So how do we, or which is the convergence criteria. So when we say that the solution that we got in the different iterations is good or not. In our case, we have usually three common convergence criteria. The first is the energy criteria. This is the most lax criteria, so it's the easiest to fulfill. And then we have criteria, convergence criteria by displacement or by force. So what is usually said is if we are doing displacement control, we should look for convergence in forces, and if we have load control, we should go for displacement convergence. But sometimes we can just go for the two and satisfy one of them. And again, it's also depending on the problem, and you should decide yourself if the solutions that you are getting using the different convergence criteria are good enough or not, or you need to be more restrict or apply more restrictions in the convergences, in the convergence criteria to get more accurate solutions. So with this, we can just say that everything in this section, and we can move to the solution method. The solution method is how the IANA is going to solve the different system of equations. So once we have a guess of our solution, we get a system of equations that we need to solve and get the displacement and stress field on our structure. So how do we solve this system is what we are going to define here. As you see in the main tree, you have again the solution method outside the execute block. So this solution method inside the execute block is going to override the selection outside the execute block. So by default, we don't need to touch anything, and we just change the overall solution method. But in some situations, we would like to get different solution methods for different execute blocks. So then we need to change inside its execute block. The one that I recommend is the parallel direct sparse, because it has now parallel computing, so you can use as much threads as you have in your computer, and then it's going to make faster the solution of the analysis. Then you have some specific configuration to get to help the solution of the system. This is not. This is how the IANA report has the different steps and the different outputs that within each iteration. So it's well, it's not really relevant. And then we can go for the output that we have a detailed video at the end of the same video tutorial. Thank you very much, and see you soon.